Lesson 3 with quadratic functions involves, first of all, what is a quadratic function? It is an equation with degree 2. It does have two variables. And the x has degree 2. The most basic equation looks like y equals x squared. And of course that varies to y equals ax squared plus bx plus c, where a, b, and c are all usually non-zero values, and they are coefficients of the terms. But when b and c are 0, we get the base equation y equals x squared. A cannot equal 0 in order to get a quadratic. A has the smallest value there of 1 in order to give us the base equation of y equals x squared. The shape of a parabola is, the shape of a quadratic is a parabola. I'll get my words right in a moment. And a parabola is just a U-shape. The basic parabola, the vertex starts at 0, 0. But a parabola doesn't have to be at 0, 0. It can shift anywhere on the x and the y axis. One of the main things that we start with when we talk about parabolas is we talk about whether a parabola is concave up or concave down. And of course that has to do with the sign of the leading coefficient, the a value. If the a value is positive, then parabola is going to open up, and so we say it is concave up because it's opening up. If the a value is negative, then our parabola is going to turn upside down and it's going to open down, and so we say that our parabola is concave down. So we also talk about this as a reflection, and it's reflecting the x-axis when the a value is negative. So we'll talk about that more when we talk about transformations, but being concave up or concave down does have to do with the sign of the a value. So just whether the leading coefficient is positive or negative helps determine whether our parabola is opening up or opening down. So a is considered our leading coefficient value. So our leading coefficient value of a is what determines whether our parabola opens up or down. The second thing that we note about quadratics is that the parabola is symmetric. That means that if we drew a line through the parabola, going through the vertex, it would divide the parabola into two equal parts, or it would mirror itself. And that doesn't matter whether the parabola is concave up or concave down, that would still happen, that line through the vertex. And so that is called a line of symmetry. And it divides the parabola into two equal parts. And again, we talked about how this line of symmetry does not matter whether it is concave up or concave down. That line of symmetry goes through the vertex. And it is denoted, the vertex is denoted by the value HK. And so the line of symmetry is always equal to the value of H. So that means that it would be X equals whatever the H is for the line of symmetry. So the equation for the line of symmetry is always the X value of the vertex. It is a vertical line, so that's why it is X equals that value. So if on our base equation y equals x squared, on that parabola, the vertex is located at 0, 0. So the line of symmetry is going to be at x equals 0, or the y-axis in this case is going to be the line of symmetry for the parabola. We talk about the domain and the range for our parabola. And we've already done this a little bit in some of our previous lessons, but for quadratic functions, the domain is generally, for every case, all real numbers. And depending on which method you use to write that, whether it is verbally, which you can use these symbols, or if you did set notation, the domain equals x such that x is a member of all real numbers. You could again do it that way. Or if you used interval notation, we would say from negative infinity to positive infinity for the domain. The range, however, is determined by the position of the parabola. And our basic parabola, since the vertex is going to be at 0, 0, our range, depending on whether we have any kind of vertical shift, is going to be y greater than or equal to 0. And then if we have vertical shifts, that range will change according to those vertical shifts. So in set notation, that would be range equals y such that y is greater than or equal to 0. And then in interval notation, that would be equal to at 0 up to positive infinity. So that would be an example in each of the various situations to write domain and range for quadratic equations. And that again changes depending on any kind of vertical shifts that may occur in a problem. So for example, if we had a quadratic equation that shifts down vertically 3 units, if we were looking at that graph, it would look similar to this. That means that vertex has changed. It is now at 0, -3. The line of symmetry has not changed. It is still at x equals 0. So that vertical shift did not change the line of symmetry. The vertical shift did not change the domain. So the domain is still -infinity to +infinity. The vertical shift does change the range, however. So the range now has shifted down like the graph has. And so now instead of being at 0, it is now at -3. So that is -3 to +infinity for the range of the graph. So vertical shifts do affect the range. It does affect the position of the vertex. Vertical shifts do not affect the line of symmetry. Reflections. We have 2 types of reflections. We have reflections over the y-axis and we have reflections over the x-axis. Now, when we have with a quadratic over the y-axis, the equation, that base equation, y equals x squared, changes to y equals -x squared. And that shows us an opposite to the x inside the square part. To visually look at that graph, however, this would be the graph of y equals x squared, but to visually look at the second graph, it really looks exactly the same because it is going to graph directly on top of the other graph. That reflection, because it is symmetric, puts the graph directly on top of the other graph. So a reflection over the y-axis is very difficult visually to see for parabolas. And other types of graphs, for example, like a square root graph, that has a reflection, that graph, which normally looks like this, when that is reflected over the x-axis, the y-axis, you can visually see that reflection occur. So reflections over the y-axis sometimes can be visually hard to distinguish with the parabola, that is one of the cases where that reflection over the y-axis is difficult to see. The reflection over the x-axis we've already talked about. That is also dealing with concave up and concave down. So y equals x squared. A reflection over the x-axis changes the sign of the leading coefficient. So the negative is outside the squared part. So our graph, which is normally y equals x squared, opening up, has now reflect over the x-axis and becomes concave down. So that is a reflection over the x-axis. It flipped from going up to flipped going down, which reflects it over the x-axis. The next type of transformation that we want to look at is how the vertical shift changes the equation. We looked at how it changed the vertex, but now we want to look at how it changes the equation. So that problem that we looked at earlier where it shifted down 3, our equation y equals x squared, to change that equation, we would have plus k here, and that represents the hk in the equation. So the k part of the vertex is going to go outside of the equation, so that makes our equation become y equals x squared minus 3, because the graph shifted down 3 to 0, negative 3. So the vertical shifts are going to change the equation on the outside of the x squared part. If the graph shifted up, then it would be a plus value to shift the graph up. So what about horizontal moves? I can't spell today. A horizontal move is going to shift the equation left or right, shift the graph left or right. So as we look at a graph, again, our basic graph is at 0, 0. So a shift that moves it 3 to the right the shape of the graph is going to remain the same. The graph only shifts to the right. That makes the vertex become, in that shift, it's going to change the x value, so that becomes positive 3. It didn't shift up or down, so that's 3, 0. Now this is the tricky part, is in the equation y equals x squared. When we put this inside the equation, we have to change the sign. We have to subtract the value of the h in the equation. So that 3 becomes minus 3 in the equation. So that becomes y equals x minus 3 squared in our equation. So in reverse, when we see an equation that has x minus 3, we have to remember that that movement was opposite that sign. It actually shifted to the right, not to the left. So a graph that shifts to the right, to the left, say 2 units, which makes this vertex -2, 0, is going to make our equation be y equals x plus 2 squared. Remember, it's minus h, so -2, and that minus makes that become a plus 2. So that's a tricky component in writing the equation for those horizontal shifts when they occur in your equation. Horizontals are the ones that are the trickiest. So we've done the vertical shifts, we've done the horizontal shifts, we've done the reflections. Let's talk about the dilations, which means the change in the sizes. If we have a change in size, then that means that we have multiplied by a particular amount. So that has to do with the leading coefficient, the size of the leading coefficient. So if the size of A, not the sign of A, but the size of A, if it's greater than 0, it's going to make the graph get larger or stretch to the y-axis. So the graph actually becomes narrower or closer to the y-axis. If the value of A is between 0 and 1, which means it's a fractional amount, then it shrinks from the y-axis. And so it actually becomes wider, or it shrinks away from the y-axis. And sometimes that's a little bit harder to detect. So that means our equation is going to look something like this. So our normal equation, y equals ax squared. If we have y equals 3x squared, then that means the graph is going to stretch by a factor of 3 towards the y-axis. If we have y equals 1/2 of x squared, that means that it shrinks from the y-axis by a factor of 1/2. So the value of the coefficient determines whether it stretches or shrinks. Now we're not going to look at horizontal stretch or shrinks, but if you were going into a more advanced class, you would also look at those horizontal stretch or shrink values. Now, to put those transformations all together, you would end up with your equation looking something like this. Y equals A times x minus h squared plus k. Each value has a particular meaning toward a movement within your graph. The sign of A tells you whether it's concave up or concave down, reflecting over the x-axis. The value of A tells you whether it is a change in the size of the graph. Is it a stretch or a shrink? The value of HK tells you your vertex. So you can always find the position of your graph in the vertex form by the value of HK. Remember, that's the opposite of that sign there. Then it also tells you your movement. So if there is a value there, it's telling you whether it moves left or right. Remember, opposite that sign. And a value in this position tells you whether the graph shifts up or down. So putting the transformations together in an equation, you should be able to predict what a graph's movement is, or if you see a graph, you should be able to write those movements into the equation for a graph. So if we had a couple of examples here, y equals x squared minus 5, this graph shifts down 5. If we had y equals negative x squared plus 3. This is a couple of transformations together. So this one reflects the x-axis, and it also shifts down too. If we had y equals x plus 1 squared minus 3, then this graph would shift opposite that sign. So it's going to shift left 1 unit, and it's going to shift down 3 units. Y equals 2 times x minus 2 squared plus 1. This particular graph is going to stretch by a factor of 2. It's going to shift to the right 2. It's going to shift up 1. So it has 3 things happening to it. So stretch by a factor of 2. It's going to shift right 2 units, and it's going to shift up 1 unit. So again, by looking at the equation and looking at knowing what each position and a value in those position does, would tell us how to predict what a transformation would be.